In this video, we're going to be talking about the sliding window technique, and more specifically, the dynamic version of the sliding window technique. So let's first revisit what exactly a sliding window is. So first, what the sliding window is it's a technique it's less than of an algorithm and more of a technique. And essentially what we do is we slide a subarray that we call a window, and this window can have static or dynamic length. And essentially what we're going to do is we're going to slide it in a linear fashion from left to right. And we're going to do this over the original array of n elements in order to compute something. And that something can be whatever you want. So let's look at an example of a static sliding window that's just going to move from left to right in a linear fashion. So here, let's say I have my array of elements 1, 3, 5, 3, 9, 6, 7, 4, and then 9. And then I have a static window that's covering 1, 3, and 5 initially. Then, once I move my static sliding window from left to right, it should look something like this. Okay, so that's the static sliding window. And in this video, we're going to be talking about the dynamic sliding window technique, and we're going to look at an example of how this can be applied and how exactly we can implement this from an O of n squared solution to an O of n solution. Okay, so let's look at the example. And the example states, given an array of n elements, what is the smallest subarray size such that the sum of the elements is greater than or equal to some constant s? So we're essentially trying to find what is the smallest subarray, right? What is the smallest window where the sum in that window is greater than or equal to a constant s. And what we're going to do is we're going to look at a specific example. Let's say, for example, n is equal to 10 and s is equal to 15. So we're given 10 elements, and we want it so that we find the smallest subarray size such that the sum of the elements is greater than or equal to 15. So in this case, if we have these elements right here, then let's think about this. Well, we want a sum that's greater than or equal to 15, and it's the smallest subarray size. Two subarray sizes that I see right here are 2 and another 2. And that's within the 5, 10, and then the 7 and 10. So I'm going to highlight the 5 and 10 here, and we're going to say that that's the answer for this current array. Another example we can see is when n is equal to 5 and s is equal to 11. We have the elements 1, 2, 3, 4, and 5. And if we wanted the smallest subarray size where the sum is greater than or equal to 11, we have 3, 4, and 5, giving an answer of 3, because that is the size of the subarray. Okay, so let's look at exactly how we might solve this problem. And what we're going to do is let's look at the naive solution first, which can be done in O of n squared time. And the idea behind this O of n squared solution, or this naive solution, is we're going to look at, for each element in the array, I, right? For each element I, we're going to iterate through all the other elements starting from I, while the sum is less than s. And then finally, we're going to stop once the sum is greater than or equal to s. Okay, so let's look at how this might look visually. So let's say I had the elements 5, 1, 3, 5, 10, 7, 4, 9, 2, and then 8. And then let's say my s was equal to 15. So I want to find what is the smallest subarray size such that the sum is greater than or equal to 15. Okay, so what we're going to do is we're going to start our index at 0. And essentially, we're going to say that this red one is I, and this blue pointer is j. And what we're going to do is we're going to start at I, right? And we're going to work our way through from left to right in the array. So we're just going to look from I to the end of the array. So what we're going to do is we're going to start a sum at 5, and the current answer for the smallest subarray size is infinity. So we're going to choose infinity so that our answer doesn't get affected later, but we're just going to update it later on so that the smallest is a valid answer. So in this case, if we see here that we move the j pointer, the blue pointer, to the right by 1, our sum increases by that amount. So it's going to increase by 1. Then we're going to move it to the right once more, and we're going to add 3 to it. So now we get 9. Then we get 14. And we're going to move this one last time over, and now our sum is greater than or equal to 15. And so now we can update our answer. We can say, okay, now the total sum in this subarray is greater than or equal to 15, and let's update our answer to be equal to 5 now, because from 1 to 10, there are 5 elements. Okay, next what we're going to do is we're going to start at the next element. We're going to start at 1 now, or index 1 in this case. Our initial sum is 1, and what we're going to do is we're going to continue moving that blue pointer over until the sum is greater than or equal to 15. So we're going to go to 3. Is the sum greater than or equal to 15? No, so add the next value as well. Keep going. And now we have a sum that's greater than or equal to 15. And now what we're going to do is we're going to update the answer variable to 4, because now the smallest has become 4. And now we can say, all right, the current answer up to this point is equal to 4. Next, we're going to go work on that 3, which is at index 2 in this array. So we can see here that the sum is equal to 3. And if we move our right pointer, the blue pointer, over by 1, we get a sum of 8. Then we get a sum of 18. So what's going to happen here? Well, we can stop looking because now we know that this is the smallest subarray starting from index 2, right? And now we can update our answer to be equal to 3. Since 18 is greater than or equal to 15 in this case, our answer so far is equal to 3. Next, what we're going to do is we're going to start at the next element, which is 5 at index 4. We're going to say the current sum is equal to 3. And we're going to say, all right, stop when the sum is greater than or equal to 15. In this case, it is greater than or equal to 15. And so we can update our answer to be equal to 2, since the number of elements in this sliding window, or in this subarray right here, is equal to 2. Next, let's work on the 10. And we can see that the 10 has a sum of 10. Move the blue or the right or the j pointer over by 1. The sum is greater than or equal to 15. And our answer remains 2 in this case. So either of these answers will be valid, the 5 and the 10, and the 10 and the 7. These are 2 valid answers, and we can pick both of them. It doesn't really matter, as long as our answer returns 2. Next, we're going to start at the 7. Move our right pointer or our blue pointer over. Now we get a sum of 11. Add the 9. Now we get a sum of 20, which is greater than or equal to 15. And we're going to see that the answer does not change because 3 is greater than 2. Work on the 4. Add the 9. So now we get a sum of 13. The sum is still less than 15. Add one more, and now we have a sum of 15. 15 is greater than or equal to 15. However, the size of our subarray is 3, which is not greater than 2. Or sorry, which is not less than 2. Let's work on the 9. We get a sum of 11 here, and then a sum of 19. And then here, what we're going to do is we're going to see, all right, the sum is greater than or equal to 15, but the size is not less than 2. Here, we can see we have a sum of 2, add the 8, and it doesn't work. Then we're going to work on the 8, it doesn't work, and so on. And so the only time it would change from now on, if there were more elements, is if the element itself was greater than or equal to 15, in which the answer would be 1. But in this case, there is none. Okay. So we get a sum of 8 here. Okay, so next, let's look at exactly how we might code this up. So in terms of the code, let's start off with that answer variable. That answer variable is going to store what is the smallest subarray size such that the sum is greater than or equal to s. Then what I'm going to do is I'm going to create a for loop that runs from 0 to n minus 1. And this is going to be the index, that target, that starting reference index that I'm going to start off on. That's that red pointer. Then for each pointer, right, for each element, I'm going to store a sum variable that starts at 0. And I'm going to create another for loop that starts at I within that for loop. So it'll start at I and then work its way to the end of the array. And we're going to have a base condition. We're going to say if the sum plus aj, right? Oh, sorry, that should be plus, not plus equals. But if the sum plus aj is greater than or equal to s, that means we can stop there. And so if we can stop there, we're going to say sum plus equals aj, right? We can add that sum to it first. And then we're going to calculate the minimum. What is the minimum subarray size such that the sum is greater than or equal to s? And now that I found it, because adding any more values from later on doesn't really do anything, we can just stop and break. And otherwise, if the sum is less than, or the sum plus aj is less than s, then we can just add it otherwise. Okay, so that is the naive O of n squared solution. But actually, let's actually examine the time complexity, just so that you understand how this is O of n squared. Because you might be saying, well, the J for loop starts at I every time. So how is this O of n squared? Well, let's look. So for each iteration, we will have to go through n elements, then n minus 1 elements, n minus 2, n minus 3, and all the way to 1 element, right? Because we're starting at I in our J for loop. And so what we can say is if we take the sum from 1 to n, we get the formula n times n plus 1 divided by 2. If we expand the n out, we get n squared plus n over 2. We get n squared over 2 plus n over 2. And because this is big O notation, we discard any of the smaller constants and we look at the largest term. And in this case, the largest term would be O of n squared. Okay. So now that we know the O of n squared, we can use the sliding window technique to improve the time complexity from O of n squared to O of n. So how are we going to do this? Well, what we're going to do is we're going to maintain 2 pointers, L and R. And what we're going to do is we're going to continue expanding our window from L to between L and R by incrementing our right pointer, that variable R, until the sum is greater than or equal to s. So we're just going to keep expanding it out while it's smaller than s, and then stop once it's greater than or equal to s. And since we want the minimum, what we're going to do is we're going to increment our left pointer, or basically shrink our window, while the sum is still greater than or equal to s. So that might not make too much sense right now. So let's look at how it might look visually. So once again, I have the same exact array, 5, 1, 3, 5, 10, 7, 4, 9, 2, and then 8. And what I'm going to do is I'm going to maintain those 2 pointers. And so let's say the blue pointer was our variable R, and the red pointer right there was the L pointer. So what are we going to do in this case? Well, what we're going to do is we're going to continue expanding our right pointer until the sum is greater than or equal to 15. So in this case, we moved it over by 1, and now it's 6. We moved it over by another 1, and now the sum is 9. Moved it over by another 1, and now the sum is 14. And we're going to move it one more time until the sum is 24. And in this case, the sum is greater than or equal to 15. And now that we have this total right here, that's 24, it's greater than or equal to 15. Well, since we're trying to find the minimum, maybe some of the elements at the front of the array aren't that necessary. So what we're going to do is we're going to shrink that L pointer by moving it over to the right. And now here's the sum is 19. Then what we're going to do is we're going to move it over right by one more. And now the sum is 18. And we're going to move it over one more. And now the sum is 15. And you can see along the way, the answer variable has been changing. It's been changing from 5, 4, 3, and now it is 2. And now that we see that we continue moving it, right? What we're going to do is we're just going to continue moving it one more time. And now the sum is just 10. And since the sum is no longer greater than or equal to 15, what we're going to do is now we're going to start moving our right pointer again. So we're going to move it over by 1, and now the sum is 17. What we notice is that the sum is greater than or equal to 15 in this case. And so what does that mean? Well, that means we're going to have to move the L pointer, the left pointer, over by 1. And now the sum is now less than 15. So what we're going to do is move that right pointer to the right until the total sum in our window is greater than or equal to 15. So move it once, the sum is 11, and then move it one more, and now the sum is 20. And so as you can see, we're going to start moving our right pointer, or the left pointer, sorry, to shrink the window as small as possible. If we move it like this, we take away the 7, we get a total sum of 13. And so what's going to happen here is now the right pointer is going to start expanding again. So it's going to expand like that. And now our sum is greater than or equal to 15. So what we're going to do is move the left pointer until the sum is less than 15. We're going to move the right pointer once more. Move the left pointer now that the sum is greater than or equal to 15. Like that. We're going to try to expand our sum once more, but it doesn't work. And then that's it. And so as you can see, the answer overall, if we kept track of the answer within each step, would be equal to 2. Okay, so let's look at how we might implement this. So first, what I'm going to do is I'm going to start off with an answer variable. This is going to store what is the smallest subarray size that the sum is greater than or equal to 15. I'm going to start it off at infinity because if in the end the result is infinity, then I know that the answer doesn't exist. Otherwise, if the answer does exist, it's guaranteed to be less than infinity. Then what I'm going to do is I'm going to store an L variable, and this L variable is going to keep track of my left pointer. I'm also going to keep track of a sum variable, which is what is the sum so far. And the reason I made this a global variable out here instead of in some kind of for loop is because this variable this sliding window technique moves linearly. So whenever we move something, it's either going to add the element at the front of the array or subtract the element at the back of the array. And so we can keep the total sum like this. Then what we're going to do is we're going to have a for loop that runs from 0 to n minus 1. And this is going to be my right pointer, my pointer r. The next step is we're going to add that pointer r, or the element at that pointer r, to our sum variable. And once we add a variable, or once we add that element to our total sum, right? If that sum is greater than or equal to s, let's continue shrinking it, right? Let's shrink that subarray as much as possible, as much as we can. And so what we're going to do is first we're actually going to calculate what is the smallest subarray size. And the way we're going to do that is we're going to say answer is equal to the minimum between the answer itself, the current answer, or is this current configuration better than the previous answer? And the current configuration would be r minus l plus 1. Then what we're going to do is we're going to take that element away from the back. We're going to say sum minus equals al plus plus. So not only are we taking away that element, we're also incrementing our left pointer by 1, so that now we're fitting everything into our window. We're maintaining that L and R pointer to be our window. And then finally, from there, what we're going to do is we're just going to return the answer. And with this, this is our total, or this is our final code. This is just a bit of pseudocode, but if you're interested in the full implementation, it should be quite translatable. Infinity in most languages can be thought of as the upper bound of your integer data type limit, or you can just put a very large number that doesn't overflow with any calculations. And so in this video, you learned about the sliding window dynamic technique.